Dear students, welcome you all to the Econometric Methods course. In the previous module, we justified the KOYCK transformation using adaptive expectations model. There is one more justification for that is available in partial adjustment model. Let us discuss the partial adjustment model in this module. This partial adjustment model is also a model of expectations, but this time the expectation variable comes in the left hand side. In other words, the dependent variable is an expectation variable. Let us go to the model. Now let us see the partial adjustment model. Partial adjustment model was proposed by Mark Nerloff. This is another justification for the KOYCK transformation. This specification is known as partial or stock adjustment model. It is assumed that there is a desired or optimal or long run equilibrium value exists. Consider an inventory model. In this model, a desired level of inventory or the long run or optimal inventory is Y star, depends on the actual sales, that is X t. We may define this model as Y t star is equal to alpha plus beta x t plus u t. Now, according to the Mark Nerloff, this Y t star, the expectational variable, is modeled. Let Y t be the actual or observed inventory level. According to Mark Nerloff, the desired level of inventory determines the actual level of inventory in the long run. So, the desired level of inventory of various time period actually determines the actual inventory level in the long run. The actual level slowly adjusts to the desired level in the long run. So, this statement can be written in the econometric model. Y t is equal to beta 0 Y t star plus beta 1 Y t star Y t minus 1 star, etc. This Y t is the actual level of inventory level based on the other expected inventory levels at different periods of time. The effect of desired level of inventory on the actual level declines with time. The impact of this inventory, the expected inventory levels, right, as time passes by, really declines. The decline is exponential. So, this may be written as beta I is equal to lambda power I beta 0, where I varies from 0 to infinity, and 0 less than lambda less than 1. So, this will exactly model this statement, the effect declines and declines exponentially. Now, based on the specification, the declining and exponentially declining effect, the equation becomes Y t is equal to beta 0 Y t star plus beta 0 lambda Y t minus 1 star plus etc. Actually, this beta 1 we substitute as beta 0 lambda, and beta 2 will be beta 0 lambda square, the term will come here, and that will be Y t minus 2 star. We can write a very equivalent equation, lag equation of this one, that is Y t minus 1 equal to beta 0, we substitute t minus 1 for t. So, that becomes beta 0 Y t minus 1 star plus beta 0 lambda Y t minus 2 star, like that it goes. If you multiply this equation, the second equation, by lambda, we get lambda Y t minus 1 plus beta 0 lambda yt minus 1 star plus beta 0 lambda square yt minus 2 star, etc. We may subtract these two equations 2 and 3. We get all the terms will go off. Actually, this is the terms, the cross terms will go off, only this first term will remain. So, we get the first term as yt minus lambda yt minus 1 is equal to beta 0 yt minus yt star. So, this is the term we will get. The long run impact in 2, this equation, the long run impact can be measured, that is nothing but sigma beta I, that is equal to sigma beta 0 lambda power I, that is equal to beta 0 can be taken outside and lambda I will be there. This will vary in I. So, we will get 1 plus lambda square, etc. It goes on. That is equal to beta 0 into 1 by 1 minus lambda, because this is a geometric series. So, the sum of this series is 1 by 1 minus lambda if lambda is between 0 and 1. So, that is equal to beta 0 by 1 minus lambda. If the impact is taken as unity or the normalized impact, then we will have beta 0 by 1 minus lambda is equal to 1. That implies beta 0 equal to 1 minus lambda. Now, the equation, the fourth equation becomes, we are substituting the value of beta 0, that becomes yt minus lambda yt minus 1 is equal to 1 minus lambda yt star. Let us take this as fifth equation. Now, we are doing some small algebraic manipulation. We are adding yt minus 1 and subtracting yt minus 1 in this equation, fifth equation. Then we get yt, actually we are rearranging the terms, and we are rearranging yt and yt minus 1 together, and we are clubbing the other things together. We get 1 minus lambda yt minus 1, the other side remains. Now, we may take this term to the right hand side. So, you get yt minus 1 is equal to 1 minus lambda yt star minus yt minus 1. This particular expression, this identity is the is otherwise represent the actual change in inventory, that is yt minus 1 is in proportion to the desired change yt star minus yt minus 1. This is otherwise known as partial or stock adjustment hypothesis. 1 minus lambda is called the adjustment coefficient, and 1 by 1 minus lambda is called the speed of adjustment. The speed of adjustment measures the number of periods it takes for much of the adjustment to take place. Now, let us multiply 1 minus lambda with 1, that is the first equation, the inventory equation. We multiply both sides by 1 minus lambda, we get 1 minus lambda yt star is equal to alpha into 1 minus lambda plus beta into 1 minus lambda xt plus 1 minus lambda ut. We are substituting the fifth equation, that is yt minus lambda yt minus 1 is equal to 1 minus lambda yt star. So, if we substitute this, that is this is substituted as yt minus lambda yt minus 1 from the equation 5. So, the equation becomes yt minus lambda yt minus 1 is equal to alpha 1 minus lambda plus beta 1 minus lambda xt plus 1 minus lambda ut. So, now we are taking this term lambda yt minus 1 to the right hand side. So, we get this equation, this yt is equal to alpha into 1 minus lambda plus beta 1 minus lambda xt plus lambda yt minus 1 plus 1 minus lambda ut. So, this may be written as simplified with simplified notations, this may be written as y t is equal to alpha dash plus beta dash x t plus lambda y t minus 1 plus 1 minus lambda u t, where alpha dash is equal to 1 alpha into 1 minus lambda, beta dash is equal to beta into 1 minus lambda. So, we are just by simplifying the notation, nothing else. Let us take this equation as 6. Let us see the equation number 6. It is quite interesting. This equation is looking very similar to the one we saw in the KOYCK transformation equation. This has got a autoregressive term. So, this compares with the KOYCK's transformation equation. This is derived not just by the algebraic reductions, but this is in fact is derived from the partial adjustment hypothesis. So, in conclusion, we will say this KOYCK's transformation equation represents the partial adjustment hypothesis, in other words. So, we can conclude the above equation compares with KOYCK's equation, and hence the partial adjustment hypothesis justifies the KOYCK's transformation equation. So, we can conclude justifies or rationalizes the KOYCK's transformation equation. So, this is one more justification apart from the adaptive expectations hypothesis that justifies the KOYCK's transformation. Now, let us take this equation number 6, y t is equal to alpha dash plus beta dash x t plus 1 minus lambda y t minus 1 minus lambda u t, where lambda dash is equal to alpha into 1 minus lambda, beta dash is equal to beta into 1 minus lambda. This equation is otherwise called the partial adjustment model. This partial adjustment model represents the short run inventory equation based on the observable variables. So, naturally this equation can be estimated using the OLS method. So, OLS procedure can be applied on this to estimate the coefficients alpha dash, beta dash, 1 minus lambda. In this estimation, you will not have any autocorrelation problem if the ut is not autocorrelated. So, naturally 1 minus lambda will also be not autocorrelated. But however, this may have some problem with this ut, and this may be related in such cases, right. This if the y t minus 1 and ut is related, then you have to use the instrumental variable method, right. Otherwise, this model will not have any problem as far as the OLS estimation is concerned. This equation is taken as the short run inventory equation. This is based on the observable variables, and so all the variables are measurable, and this model will not create any problem in the practical sense. So, from this equation, the alpha dash and beta dash, right, we may estimate alpha and beta, because alpha is nothing but alpha dash by 1 minus lambda. Beta can also be estimated because beta is equal to beta dash by 1 minus lambda. This 1 minus lambda is just the coefficient of y t minus 1. So, if you divide this alpha by the coefficient of y t minus 1, and if you divide the coefficient of x t, that is beta dash, by 1 minus lambda, you will get alpha and beta respectively. Along with that, you may estimate the standard errors of these estimators. So, that is also very simple. Actually, I have got a formula. So, with those formula, we can estimate the standard errors of alpha and beta also. So, in that case, once the model, this a partial adjustment model is estimated, you can retrieve actual the inventory, the desired level of inventory model can be estimated. So, the desired inventory model can be estimated with this partial adjustment model. Now, this equation number 1 is derived from the equation number 6, but now this has got far beyond the application than just the justification for the KOYCK transformation equation. This long run and short run relationships are of great interest to the theory. Now, let us take an example and see the long run and short run equation relationships, the parametric relationships and the speed of adjustment. For that we can take one example from the usual econometric books. I have taken one long run demand model. In this long run demand is a function of the interest rate and the real GDP. So, this is the model, and this model with the help of quarterly data it is estimated. So, this quarterly data based model is first fitted for the partial adjustment model, and the partial adjustment model corresponding to this long run demand for money is ln MT as a function of ln RT, ln GDP and ln MT minus 1. Actually, this is the first lag or the autoregressive term of the dependent variable. So, this model is estimated. The model we can see best fit model R squared is very high, and the model is significant, and most of the coefficients are significant actually, except the one for the GDP, right. The remaining coefficients are significant, and so the model can be interpreted comfortably, but we have to be very careful. This all these variables are in logarithmic scale, and so the coefficients have to be interpreted as the elasticities. The marginal interpretation has to be based on the elasticities. So, each of this coefficients represent the elasticities, respective elasticities of demand. Okay. Now, this the coefficient of log MT minus 1 will give you the lambda coefficient. From this lambda coefficient we can find the 1 minus lambda. So, first we will see the 1 minus lambda. This is lambda is 0.9607, and if you subtract from 1 we get 0.0393. So, this is the 1 minus lambda measure. This 1 minus lambda can be we can divide this 1 minus lambda in all these coefficients to get the long run coefficient measures. So, the long run coefficient measure 0.8561 can be divided by 0.0393 to get 21.79. This is the coefficient of the long run demand function, long run demand for money, and this is the coefficient you got for the ln RT. We just divide 0.0634 divided by 0.0393. So, you get this coefficient, and the third coefficient is 0.0237 divided by 0.0393, you get this coefficient. So, this is the long run equation which gives a equilibrium equation. Now we can interpret this coefficients. This speed of adjustment, the coefficient of adjustment 0.0393 represents, actually this can be approximated to 0.04. So, 4% of discrepancy between the desired or long run cash balance is eliminated in a quarter. So, the desired and the actual cash balances is eliminated. The discrepancy between the desired and actual cash balances is eliminated by 4% in a quarter. So, that is the interpretation. And we can also compare this elasticity measures of short run and long run equation. The long run interest elasticity of demand for money, that is 1.613, is substantially greater than the corresponding short run elasticity of demand for money, that is 0.0634. So, this is very very high. That is what we can interpret from this example. So, what we can conclude is from this partial adjustment model, we get short run and long run equations of demand, and also this short run equations in fact represents the partial adjustment model, which is very much like the KOYCK transformation equation, and so the KOYCK transformation equation is theoretically justified by the partial adjustment model. So, this is the interpretation of this model. This is the concluding module of the unit that discussed the dynamic models. In the last 5 modules, we discussed the estimation methods of distributed lag models and their theoretical connections. Today, in this last module of the unit of dynamic models, we saw the justification for the KOYCK's approach to estimating distributed lag model. The KOYCK transformation equation represented the short run relationships corresponding to the long run relationships expressed in the model of expectations. You may find a lot of examples in the referred textbooks which would give you a good understanding about the dynamic models. I hope you would have learnt more about the dynamic models in the last 5 modules. Thank you for watching. Goodbye.